Welcome back to Physics 191. I'm Gerard Blanchard. This time we're going to continue our discussion of Newton's universal theory of gravity, where gravity depends, where the gravitational field depends on the distance that you are from the center of the Earth. And we're going to talk this time about another case of things that go up and don't come down, and that is objects that orbit the Earth. The simplest possible orbit, or the simplest for us to deal with, is a circular orbit. In this diagram, you can see a mass, m. We're not going to specify what the mass is yet, and you'll see why in a second. We have a mass m orbiting the Earth in a circular orbit. Since it's moving in a circle, let's assume that it's moving at constant speed. Then there is an acceleration towards the center of the circle. Remember this from circular motion. An object that moves at constant speed in a circle is accelerating because although the magnitude of its velocity is constant, the direction is changing. So if we look at Newton's second law for this object, the acceleration on the mass is equal to the total force on the mass divided by its mass. The acceleration is the radial acceleration, or the acceleration towards the center of the circle, which I'll write as AR. And that's equal to the gravitational force, which is equal to mg divided by m. AR, the radial acceleration, will replace by v squared over r. And on the right-hand side, we have mass divided by mass, which gives us 1, and we don't have to write that anymore, times g, which we'll write as big G, times the mass of the Earth, divided by the distance that we are from the center of the Earth squared, which is r squared, the radius of the circle squared. And you can see that m's become 1, and one of our r's on the left-hand side of the equation cancels off with one of the r's on our right-hand side of the equation, and we take the square root of v, and we see that the orbital speed, the constant speed with which the object moves around the circle, is equal to the square root of big G, our gravitational constant, times big M, the mass of the Earth, divided by r, the radius of the circle. So the orbital speed depends only on the distance that we are from the center of the Earth, assuming that we're orbiting the Earth. If we were to change to a different planet or orbiting around the Sun, then we would change the big M, the mass of the primary object, to reflect that. But for an orbit around a given object, the orbital speed depends only on the radius of the circle, the radius of the orbit. Now you'll notice that M canceled out. The mass, the orbital velocity, or the orbital speed, does not depend on the mass of the object. So any object will orbit at the same speed for a given radius of the orbit. And that explains why things, say in the space station, the International Space Station, seem to be weightless. What's really happening is that they're all orbiting together. They're all orbiting at the same speed, so they don't move relative to each other. You might ask, are they really weightless? Do they not have any weight? And that's not correct to say that they're weightless. They have weight. There is a gravitational force on them. Otherwise, they would not move in a circle. They would move in a straight line. So there has to be weight to keep them orbiting. It just so happens that the weight of each is directly proportional to its mass. So they're all accelerating together around this circle, which also means that they're all moving at constant speed around the circle. So an object that is orbiting is indeed falling. It's just not falling towards the Earth, it's falling around the Earth. Now, one other property of an orbit that we're interested in is the period of the orbit, or the time that it takes to complete one orbit. Well, from our circular motion equations, we know that the orbital speed will be equal to the radius of the orbit times the angular speed, or V is equal to R times omega. For V, the orbital speed, we can substitute in the square root of big G times big M over R, and that's equal to R times the angular speed. The angular speed would be 1 revolution per 1 period, which I'll write as 2 pi radians divided by big T being the orbital period. And we can solve that for the orbital period is equal to 2 pi times the square root of the radius of the orbit cubed divided by big G and big M. So once again, the orbital period depends only on the radius of the orbit. It doesn't depend on the mass of the object. And you can also see that the further out you go, the bigger R is, the longer the orbit will be. And at some point, you will get an orbit that's exactly 24 hours in period, and so it will orbit the Earth at the same rate as the Earth rotates, and that satellite will stay directly above one point on the Earth, and those are called our geostationary satellites. Well, let's put this to work. Let's work some exercises. And the first question is, a spy satellite is in circular orbit around Earth. It makes 1 revolution in 6 hours. How high above the Earth's surface is the satellite? So remember that the radius of the orbit is not equal to the height. The radius of the orbit is the radius of the Earth plus the height above the surface of the Earth. Okay, please answer that question. Here's the Earth, has a radius RE, and the satellite is orbiting the Earth at some height, h, above the surface of the Earth. So the radius of the circle, the radius of the satellite's orbit, R, is equal to RE plus h. So be careful of that when you're working these orbit questions. Sometimes it depends on the reference point. Sometimes you'll be asked for height, and sometimes you'll be asked for the radius of the orbit. Just be careful about what you're asked for. Okay, here's the spy satellite. It's orbiting. The period of its orbit is equal to 6 hours. And we convert that to our basic metric units. There are 60 minutes in 1 hour and 60 seconds in 1 minute. That would leave us units of seconds. And what is that equal to? That's equal to 6 times 60 times 60, and that is 21,600 seconds. And that is all of the information that we have. So we'll use our equation for the period of the orbit. period of the orbit is equal to 2 pi times the square root of the radius of the orbit cubed divided by big G times big M. And so we'll divide the period by 2 pi and then square that. So T orbit divided by 2 pi, and we'll square that, is equal to radius cubed divided by big G times big M. And so big G times big M times T orbit over 2 pi squared is equal to R cubed, and we'll just have to take the cube root of everything to get R. And so that would be, let's go ahead and calculate that. That would be we go ahead and write that out. The cube root of Gm times T orbit over 2 pi squared is equal to R. Okay, now we'll need some room for our calculations. Big G is 6.674 times 10 to the minus 11. And mass of the Earth is 5.97 times 10 to the 24 basic metric units. T orbit is 21,600 seconds divided by 2 pi, and we'll square that, and then we take the cube root of all of that, and that will equal R. Okay, let's see. I'll take the cube root of 6.674 times 10 to the minus 11. 6.674 times 10 to the minus 11 times 5.92 times 10 to the 24 times 21,600 divided by 2 times pi, and I will have to square all of that, and that will give me the radius of the orbit, and that will give me 1.67 times 10 to the 7 meters is equal to R. 1, 2, 3, 4, 5, 6, 7. Yes, 1.67 times 10 to the 7 meters is equal to R. And 1.67 times 10 to the 7 meters is equal to the radius of the Earth plus the height. So 1.67 times 10 to the 7 meters minus the radius of the Earth, which is 6.37 times 10 to the 6 meters, is equal to the height. And so from my 1.67 times 10 to the 7, I will have to subtract off the radius of the Earth, which is 6.37 times 10 to the 6, and I'm left with 1.03 times 10 to the 7 meters is the height, or the altitude of the satellite above the surface of the Earth. And that is the answer to the question that we were asked. Okay. Now let's talk about getting a spacecraft or getting any object into orbit around the Earth from the surface of the Earth. To do that, you have to do two things. You have to lift the object up to the appropriate altitude or the appropriate height, and then you also have to give it enough speed to keep it moving in orbit, otherwise it'll fall back down. So let's ask a question that addresses that point. How much energy does it take to launch the space shuttle, which we'll assume has a mass of 2 million kilograms, from the surface of the Earth to a circular orbit at an altitude of 300 kilometers? Now, when I ask how much energy does it take to launch the space shuttle, what I'm asking for is how much non-conservative work does it take to launch the space shuttle. It takes non-conservative work to launch the space shuttle in the form of the rocket thrust doing work, and that's energy that you don't get back when the shuttle comes back down to the surface of the Earth. The only energy we get back is the conservative energy, which would be the gravitational potential energy. So this is a question of how much non-conservative work does it take to put the space shuttle into orbit. So go ahead and answer that question. Okay, here is the Earth, and here is the space shuttle, a square space shuttle, sitting at rest. So V initial is equal to 0, and R initial is equal to the radius of the Earth, and it gets launched, and it winds up in orbit with V final is equal to V orbit, and R final is equal to the radius of the Earth plus 300, and I'll go ahead and convert those kilometers to meter. Well, 300 kilometers, and there are 1,000 meters in 1 kilometer. Okay, and the radius of the Earth is 6.37 times 10 to the 6 meters. So R final would be 6.37 times 10 to the 6 plus 300,000, and that would give me 6.67 times 10 to the 6 meters for R final. V orbit, we can calculate V orbit. We'll come up here. V orbit would be the square root of big G times the mass of the Earth over the radius of the orbit, which is equal to, big G is 6.674 times 10 to the minus 11 times the mass of the Earth, 5.97 times 10 to the 24 divided by the radius of the orbit, which is 6.67 times 10 to the 6, and we have to take the square root of that, and we get V orbit is equal to the square root of 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by 6.67 times 10 to the 6. And I get 7,730, we'll call it. Well, I've rounded off. 77. Actually, let me round off a little bit less. Let me call it 7727 meters per second. So V orbit is 7727 meters per second. And the only thing I've left out of this is the mass of the space shuttle. And we said that the mass of the space shuttle is 2 million kilograms. Okay. And that is all the modeling of the situation. Actually, we haven't finished modeling the situation because we haven't written out our starting equation. Our starting equation is our energy equation. This is a change in position and a change in speed. And so our energy equation is work non-conservative is equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. We know that kinetic energy initial is 0 because the space shuttle starts from rest. Work non-conservative is not 0. That's the work done by the boosters, the thrusters, that the rockets that launch the space shuttles. They exert a force. The gravity is not the only force on the space shuttle. It's the thrusters as well. We are ignoring air resistance, however, which we really couldn't do in reality. Well, what do we have here? We have work non-conservative is equal to 1/2 mv final squared plus the final gravitational potential energy, that's minus mass of the shuttle times big G times mass of the Earth, big M, divided by R, minus over R final, that is, minus our gravitational potential energy initial, which is minus little m, big G times mass of the Earth over R initial. Okay. What I'm going to do is I am going to factor out everything here that we have the same. We have let me write that out, work non-conservative is equal to 1/2 mv final squared. We have a minus little m, big G, and a big M. So minus m, big G, m, minus m, big G, and m. And then all I'm left with over here is 1 over R final. And here I have minus 1 over R initial. So I haven't changed anything because I still have minus m, big G, m, divided by R final. And then I have minus negative big G, big M, divided by R initial. So I've just factored it out to make our calculations a little bit simpler. But now we have to do our calculations. Work non-conservative is equal to 1/2 times 2 million times V final squared, 7727 squared, minus the mass of the shuttle, which was 2 million, times big G, which is 6.67 times 10 to the minus 11, times the mass of the Earth, 5.97 times 10 to the 24, and then times 1 divided by R final. So it'd be 1 divided by 6.67 times 10 to the 6 minus 1 over R initial, which would be 6.37 times 10 to the 6. And then close my parentheses. Okay. And this is 6.67 times 10 to the 6. That's R final. And this is minus 1 divided by 6.37 times 10 to the 6. That is R initial. Okay, so now it's time to get your calculator out and calculate all of that. We have 1/2 times 2 million times 7727 squared minus 2 million 1, 2, 3, 4, 5, 6 times 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 and then then times, and parentheses, 1 divided by 6.67 times 10 to the 6 minus 1 divided by 6.37 times 10 to the 6, and that gives us 6.53 times 10 to the 13. So work non-conservative is equal to 6.53 times 10 to the 13 basic metric units of energy, which are joules. So that is the non-conservative work that must be done in order to launch the space shuttle. Now I have one last question about orbital energy, and it deals with the energy required to change an orbit. And the reason I put this in is because you're going to be doing very similar exercises when you go into Physics 192 and you talk about changing the orbit of an electron around a proton. This is something that you might have also done in chemistry when you've talked about the energy that it takes to change an electron in its orbital. And it's all related, as we'll talk about very shortly. So, our question is, how much energy would it take to move the space shuttle with a mass of 2 million kilograms from a circular orbit at an altitude of 300 kilometers to a circular orbit at an altitude of 400 kilometers? Once again, what I'm asking for is the non-conservative work required to change the orbit. And you can also use the value, some of the values that we calculated in our last exercise to make things go a little bit quicker. So please answer that question. Okay, here's the Earth. Here is our 300 kilometer orbit, And here is our 400-kilometer orbit, not drawn to scale. And here is the space shuttle. Initially, we've already calculated what that is. That would be 6.67 times 10 to the 6 meters. That was our final from our last exercise. And our V initial is the orbital speed at 300 kilometers, and we've already calculated that. That was our V final from our last exercise, and that is 77.27 meters per second. And we want to move the space shuttle into an orbit with R final equal to the radius of the Earth plus 400 kilometers. And so that would be equal to 66.37 times 10 to the 6 meters plus 400,000 meters, and that would actually be 6.77 times 10 to the 6 meters. It's 0.1 times 10 to the 6 higher than we started, so all I did was add 0.1 times 10 to the 6 to this number right here. And V final, we will actually have to calculate. So that's R final. V final is equal to V orbit, which is equal to big G times the mass of the Earth over R final. I'll call it V orbit final. And take the square root. And that's equal to 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by 6.77 times 10 to the 6. Take the square root. And what does that equal? The square root of 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by 6.77 times 10 to the 6. And that is 7.669 meters per second. So it's orbiting a little more slowly. So we'll reduce our kinetic energy by a little bit, but we'll increase our potential energy by more. So it'll take a net positive amount of work to lift the space shuttle up into its new orbit. And the only thing I haven't put in is that the mass of the space shuttle is 2, and I'm going to write that as 2 times 10 to the 6 kilograms, just to make things a little bit easier to work with. Don't have to write all those zeros. Okay, this is an energy situation, and our equation is work non-conservative is kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. And we have now modeled our situation. It's just time to solve the equations. So work non-conservative is equal to 1/2 mv final squared minus 1/2 mv initial squared plus minus gm over r final minus gm over r initial. That's k final minus k initial plus U final minus U initial. And once again, to make our calculations a little bit easier, I'll write that as work non-conservative. And here I have, I'm sorry, I actually left off something right here. I've left off my mass of the space shuttle. Yeah, so the space shuttle is minus mg big M over R final. Okay, so I have 1/2 m times V final squared minus V initial squared minus mass of the space shuttle, big G, big M, times 1 over R final minus 1 over R initial. So I haven't done anything there except to factor out our common terms. And that leaves us with work non-conservative is 1/2 times 2 times 10 to the 6 times 7669 squared minus 7727 squared minus 2 times 10 to the 6 times 6.674 times 10 to the minus 11 times the mass of the Earth, which is 5.97 times 10 to the 24 times 1 over R final, 1 over 6.77 times 10 to the 6 minus 1 over R initial, which would be 6.67 times 10 to the 6. Okay, time to calculate. And we will get work non-conservative equals. Okay, 0.5. Okay, 1/2 times 2 times 10 to the 6 times 7669 squared minus 7727 squared minus 2 times 10 to the 6 times 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 times 1 divided by 6.77 times 10 to the 6 minus 1 divided by 6.67 times 10 to the 6. And that gives us 8.71 times 10 to the 11 units of energy, which are joules. So it took us 6.53 times 10 to the 13 joules to get the shuttle up to an orbit of 300 kilometers, and a small fraction of that, 8.71 times 10 to the 10 joules, to raise it another 100 kilometers. Okay, well, those are our exercises using Newton's law of universal gravity. Now, I've had a particular reason for holding off on these sections, on the section of the book dealing with Newton's law of universal gravity, until the very end of this course. And the reason is because it segues very nicely into what you'll be doing when you first start Physics 192. The first thing that you'll deal with in Physics 192 are electric forces and fields and energy. And they are very, very similar to Newton's law of universal gravity in terms of forces and fields. So electricity is also a field force, and the electric field is equal to a constant K, which is called Coulomb's constant. This is similar to Newton's gravitational constant. Coulomb's constant is 8.988 times 10 to the 9 kilograms meters cubed per second squared Coulomb squared, times big Q, which is the charge, the electrical charge, that's our analog to mass now, times the electrical charge of the object creating the electrical field, divided by r squared, which is the distance that you are from the center of the object creating the electrical field. So you can see that this is very similar to little g is equal to big G times big M over r squared. Both electricity and gravity are field forces, and they obey the same equations where you change the constant. There's a different constant for electricity and a different constant for gravity. And you change the property of the object that is creating the field. A mass creates a gravitational field. Mass creates gravity. Mass creates a gravitational field. Electrical charge creates an electrical field. So mass creates a gravitational field, and electrical charge creates an electrical field. Now, similarly, it is mass that feels a force from a gravitational field, and electrical charge that feels a force from an electrical field. So we'll look at that equation again. The electrical field is equal to our constant, which is K now, times big Q, the charge that is creating the electrical field, divided by r squared. That's exactly the same. The unit of charge is the Coulomb, big C. Big C is a Coulomb. And that is how we measure charges. Just like masses have a certain number of kilograms of mass, charges have a certain number of coulombs of charge. And if you work out the units of the electrical field, you'll see that the unit of the electrical field is newtons per coulomb, or in other words, newtons of force per coulomb of charge that is feeling the electrical field. That's why very long ago I wrote gravitational field in units of newtons per kilogram, because a mass in a gravitational field feels a force, a certain number of newtons of force per kilogram of mass. Similarly, for electrical fields, the electrical field exerts a certain number of newtons of force per kilogram of charge feeling the force. The electrical force is little q, which is the charge feeling the electrical force, or the feeling the electrical field, times E, the electrical field strength. This is similar to gravitational force, or weight, being equal to mass times little g. So now it's not the mass of the charge that feels the force, but the charge that feels the force. So electrical force is charge times electrical field strength. Very similar to what we've done. And finally, you're going to see an equation for electrical potential energy that is very similar to our Newton's universal law for gravitational potential energy. And that is the electrical potential energy is equal to little q times our constant K times big Q, the charge creating the field, divided by R. The only difference here is that we don't have the minus sign. And the reason why we don't is that the charge itself can have a minus sign. Mass is always positive, but charges can be positive and negative. And the force will be attractive when the two charges have different signs. So the charge itself will provide the negative sign in electrical potential energy. So that is actually the end of new material for Physics 191. We will have 2 more lessons in which we review all of the major concepts in Physics 191. So next time, we'll start off with that review. Until then, think physics.